What I wanted to talk about today is one of my sort of favorite test problems, one of my favorite sort of basic, simple examples that I have in my head when I'm thinking about neural network optimization and neural networks in general. So the motivating idea here is that neural network optimization is really complicated. It's got a lot of pieces to it. And even though it might feel easy now, it's not actually that easy of a thing to do. So, nowadays we've got so many good architectural ideas. We've got so many good just sort of, built-ins in the neural network libraries that we use, like PyTorch and TensorFlow, that it doesn't strike us as that difficult to spin up a neural network and train it on something like image classification. And this is something that the Optimization for Deep Learning review paper by Ro Yu Sun at U of I handles really, or mentions, and I think makes a good point about, that if it was 1980 and you sat down to try and solve an image classification problem with neural networks, you probably would fail because you don't have all these nice things in your toolkit that we have. And so because of that, I think it's easy for us to forget that there's a lot of complexity underneath something like .fit. And so when it comes to trying to understand something difficult in mathematics, which is in the end, I think, one of the best ways to understand what's going on in deep learning in this, numerical computing kind of field, I think the most important thing that is underappreciated by people who come from a software background is the importance of simple test problems. And so I think there's a really great explanation of this that I got from a friend who finished their PhD in math at Berkeley around the same time I was doing mine. And what they said was, everyone I know who does math does basically the exact same thing to make their lives easier. Whenever they hear a conjecture, somebody's thought about how something might work in some branch of math, they compare it to two examples specific to that branch. One that's well-behaved and simple, and another that's pathological and counterintuitive. And if the conjecture is true on both, then it's probably true. And if it's not, then you've got yourself a nice counterexample. So when it comes to trying to understand and think about machine learning, like what's going to work well, what's going to not work well, why to use a particular piece or why not to use a particular piece, or if somebody makes a claim about the nature of deep neural network training, I use the same tactic. And so my two examples, one of them is memorization tasks. That's one of my pathological test examples, that if somebody makes a claim about how neural networks work and how they generalize, I think, okay, does this explain memorization in neural networks well? So specifically, a memorization task is one where you destroy all structure relating the inputs to the labels. So if you were to take, say, the MNIST data set, and then instead of having the actual targets, you just shuffle them. So this little bit of Python code here takes the MNIST targets and replaces them with a shuffled version of them. Turns out neural networks can still minimize the training loss in this example, even though there is no, there's no information there anymore. It's just the labels are effectively random. So this is something that people have demonstrated, and it shows that neural networks are capable of memorizing their data sets, even if they don't necessarily do that in real life. So the two sides of this coin are, you have one example that's sort of the canonical gnarly bad example, and then you have one example that's the well-behaved and simple example. And for me, I use one that is effectively just multiplying by one with a deep neural network. So let's go through this. It's got a mathematical inspiration, and so I took a mathematical approach here. So a fully connected network, let's define that. It's a function of its parameters and its inputs that alternates between matrix multiplication and function application. So it's got all these nonlinearities, sigma 1, 2, up to k, and then it's also got these parameter matrices, theta up to k. And we alternate between applying the matrix to the input and then applying a function to it, a possibly nonlinear function to it. An autoencoder network is a specific type of network, one that compares its outputs directly to its inputs as opposed to comparing them to something else. So D is some function that takes two inputs. If they're the same, it returns 0. Otherwise, it returns something else. And what D is doing here is it's comparing the input X to the output of the network, F applied to its parameters and its input X. And that function there that I'm defining here through this is the loss function. It says, okay, the loss function compares the inputs to the outputs. And the loss is what we make small, and an autoencoder, therefore, returns something that's close to its inputs. So the case of autoencoders includes just multiplying numbers by 1 as an important special case. So if we just take all of those functions to be the identity, right, just take all the nonlinearities out of our neural network, we'll end up with something called a linear network. And linear networks, I'm not the only one who likes to use these as a test case for doing theory on neural networks or for thinking about neural networks. So there's a nice paper by Sachs, McClelland, and Ganguly that's basically what can we do to understand not only how neural networks learn, but actually a little bit of the psychology of how animals and humans learn just by studying what happens in linear networks. It's also the case that networks with rectifying linear units are actually piecewise linear on their inputs. So this gives you a sense of like, okay, if I only change the input a little bit, a rectified linear network will behave very close to a linear network. So it's another reason why this case is useful for helping you build your intuition about what's going on. The difference being that because it's simple, and because it's dropped that nonlinear piece, it's a lot easier to understand. So if we also take another step and make this even simpler and choose the dimension of everything to be 1. So every hidden layer has dimension 1, the input has dimension 1, and so the output has dimension 1. We replace all that matrix multiplication with just a series of things multiplying together. And we get a function looks a little bit like this. I was using this case actually to help me understand JAX better. So that's kind of where this talk came from. And so in JAX style NumPy, that looks like, okay, f of theta and x takes the product of all the thetas and multiplies them by x. It's the same thing as what's written above. And it's got this nice little bit of extra JAX stuff here to make it so that I can now apply this function on a single input or multiple inputs, so batch or non-batch, and I can apply it to one parameter set or many parameter sets all at once. So I can effectively apply 10 networks to 10 data points and get 100 outputs with just the same function that I can use for normal forward prop. So JAX is pretty great, is one thing I learned in the process of building this example. So the reason why I wanted to do this simple setting, and one of the things that makes this a really powerful example, is because it's so simple that we can actually see everything that we normally can't see when we're doing deep learning, for real, when we're doing it on images with thousands of pixels in them and trying to predict one of thousands of classes at the end. The dimension of everything is so big. The dimension of that input X, the dimension of the hidden of the parameters theta, these things are in the thousands, in the millions, in the billions nowadays. And so you're hosed for trying to think about that spatially and for trying to visualize it. But if we, in this case, choose the number of hidden layers to be 1, so there's one hidden layer, and then one output layer, and so 2 layers total, then we've reduced this down so much that now there's only essentially 2 dimensions, 2 parameter dimensions to think about. And so anything that has to do with the parameters, we can visualize. We can visualize because we have 2 dimensions for the parameters and then 1 dimension for whatever it is we're trying to measure. So for example, we can look at the network's output as a function of the parameters here. So this is a surface here. So the values there, it gets red as the value gets higher and it gets blue as the value goes lower. And then in between it is gray. And that z-axis, which is also the color axis, is the output of the network on the number 1. So if I put in the number 1 to this network, what do the outputs look like? And it looks like the outputs get big as the parameters have the same sign. So as we go to 2, 2 in the upper right quadrant, and it gets, and similarly, the output gets big if both inputs if both parameters are negative and large. That's the bottom left corner, which is also red. So in order to finally get a loss function and get ourselves to the point where we're looking at a neural network optimization problem, we just need to choose that difference there, that D function that compares the inputs to the outputs. And so if we choose the squared error, then the loss function is just the squared difference between the inputs and the outputs averaged over a batch. That's easy to code up. We just apply the mean of the squared error function like that. And that loss is actually simple enough that it's something we can write out explicitly. So if we just say, all right, let's say that our only input is the number 1. There's only one data point. Then if we look at that as a function of theta, let's see what the loss looks like. So first, theta 1 times theta 0 times 1 is what f of theta colon 1 is up there, theta semicolon 1 up there is. That's the definition of what our network does to its inputs. So that simplifies things. And then we can take that and write it out, sort of expand it out if we'd like. It makes it a little bit easier to do other manipulations. And it's very clear now that this is just a polynomial, right? And that's helpful, especially if you have a bit more of a math background, to recognize something that you may have seen in other places in mathematics, in other problems that you've run into. You've probably run into polynomials before, whereas neural networks are maybe a new and curious thing. On the other hand, maybe if you know a little bit less about math and are a little bit less comfortable with polynomials, it's interesting to see that the simplest version of a network, of a neural network, ends up being a polynomial in terms of its loss function. So not only can we write it out explicitly, we can also sort of look at it. We can directly look at it. We can visualize this loss function. So this is the thing that we are moving on when we do gradient descent. This is the thing that we are, because it's in 2D with this one extra dimension, it's sort of a lot more physical, right? It looks a little bit, if you look at it, like a mountain range, right? There's two of those two big red mountains coming up off the side, a nice big valley in the middle. It's a little bit more physical, and we can think about it in these sort of more physical terms. And this, in a way that we couldn't if we were looking at a neural network problem where this is tens of thousands of dimensions. And even more so, we can also combine that with by hand mathematical calculations to get the values of the gradient. So if you crank through that polynomial that we had previously, you can calculate the gradient by hand. Uses only the rules of the gradient calculus for polynomials, which are on the easier side of calculus when it comes to doing calculus. And you can actually get an explicit expression for the gradient. Of course, in Python, we rely on automatic differentiation, but it's helpful, especially in cases where we use automation to take some of the difficulty out of the actual problems we want to work on, to be able to go back to a simple problem like this one and actually crank it out, work on it step by step, and see what exactly is being automated away. And the utility here is that we can actually then look at not just the loss, but also the gradient as an overall vector field. We can look at what the gradient is at every single point and get a better sense maybe for how gradient descent is going to behave. So you can see, if you take a look at this gradient field a little bit more closely, the highest values are very far away from the center, and then the values drop precipitously. So these little tiny arrows represent the gradient at each point. They point in the direction gradient descent would go, so it's the negative gradient. And these, you can see that they're much, much tinier as we get down to the bottom here. So the gradient, the scale of the gradient, it gets really, really big when you're far away from a solution. And then once you get even a little bit close to it, it shrinks back down. So this is something that's going to generally be the case with neural networks. And this is one of the reasons why your loss goes down really, really quickly when you first start, because you tend to start in some area where you're not doing so well. And there's obvious, big gradients that help you improve really, really quickly. So gradient descent is the method that gets used to optimize neural networks, right? We take that gradient and we apply it, we calculate it, take it, scale it, flip it around, and add it to the value of the parameters. So we follow those arrows there that I was showing on that on the surface. And so that looks like, in Python code, it's theta minus eta times the gradient. And it took JAX here, and I actually vectorized that function, which gives you the ability to run gradient descent on multiple networks across batches at the same time, all with the same function that you would use to train one. Again, JAX has some pretty cool stuff in it. Though I feel obligated to point out that some things are a little bit harder in JAX, namely that if you want to try and update the values of the matrix, say pre-allocate memory and then touch it later, JAX makes that a little bit harder. So, I felt like I couldn't be completely positive without pointing out the one place I ran into some trouble. But, that tiny bit of trouble aside, that little detail avoided, it was, straightforward to set up this nice batched gradient descent. So to run gradient descent for a couple of hundred steps from a couple of hundred different positions was pretty fast. And that gave me this visualization here on this one. And you can see a large number of the trajectories are getting sucked towards the center there. So they're getting sucked towards the value 0, 0 right in the middle at the origin. So multiplying the inputs by 0, and that's not what we wanted to do, right? We wanted to get a solution where we multiplied the inputs by 1. We want the inputs and the outputs to match one another. And so just looking at this one, it would look like, okay, well, there's, sometimes when I do gradient descent, it's going to fail on this problem, and sometimes it's going to succeed. And so we can see that if we take a look at the losses over time. So this is the kind of plot that you're maybe actually able to do when you're doing, machine learning at scale. You can just plot the loss that you calculate through training. And so this looks, actually quite different from what you would see during training, in that there are, all these traces that are not converging down to the lowest values. And this is just across different initializations. But when we work with typical neural networks, we use random normalized starting positions, right? We don't start on these special grid positions. So we need to randomly initialize things, and just for fun here, randomly doing things in JAX is actually quite a bit more challenging than it is in other frameworks. You have to be very explicit about where you're being random and non-random. But once I did that, it was pretty straightforward to do once I figured out how to do that, it was pretty straightforward to do random initializations, and things look actually quite a bit different. So this is, I think, the same number of initial trajectories, or at least the same number as the number that I plotted the loss of before. But now we can see that actually, none of them are going towards that center value, and all of them are actually starting off at lower levels and going down to at about the same height. So this is also something that we see in other neural networks, in bigger neural networks, so long as we're careful to randomly initialize and we're careful to set that scale in a thoughtful way. So to make sure that things are not just random, but also normalized. If you look at the starting positions of those, you'll see they form a nice circle in the XY plane. And training looks much better. It looks, they all seem to be going down to the same value of the loss. Perfect score of 0. Seems like things are going in that direction. And one interesting thing here is that you can see one gets a little bit stuck. So it heads towards that center there, actually. Maybe if we head back a slide, you can see that a couple of these trajectories head towards the center of the they head towards the center of the parameter area, and they before heading down and joining the rest of the trajectories that are going to the correct solution. So that's what this trace here represents. That's one of those examples, and this is something that we do also sometimes see when we're doing when we're applying neural networks at scale. We see sometimes there are trajectories which get stuck for a while before jumping off of a cliff. So it seems like they're probably doing something kind of similar to what's happening in this problem, where there's a solution that is close to the that looks kind of like this one, that has this kind of Pringle shape, where in one direction the loss goes up, and in one direction the value goes down. Okay, so that's another little phenomenon that we can see in this simple problem. So due to the simplicity of this loss, we can actually also calculate all the possible solutions. So at all of the solutions, it will be the case that the gradient is 0, right? So we want the gradient to go down over time as we're optimizing, and that when the gradient is 0, that could be because we're at a solution. At least all solutions will have gradient 0. So let's check what are some values that'll give us gradient 0. Well, we'll apply it to that to the value of the gradient, which we can calculate by hand. It's relatively straightforward. I skipped the math here just to keep things going forward. And unsurprisingly, it's going to happen when theta 1 and theta 2 are multiplied together equal 1. So that means that if we multiply the input by those values, we'll get 1. We'll get the same value out as in. And so those are our solutions. And we can actually calculate those. And the code there at the bottom now shows the how you would calculate the positions of all of those solutions, x and 1 over x for positive values of x and for negative values of x. And now we can actually visualize that solution set. So we can see that what's happening is that gradient descent is taking us towards that solution, and not towards that the value in the center where both of the parameters are 0. So we can see that they're landing at different points on that solution set. And interestingly, they're landing on both the values that are positive and the values that are negative, depending on where they were initialized to. So the interesting thing about that solution set is basically one corresponds to flipping the value and then flipping it back to multiply by 1. And one corresponds to just, multiplying it by 2 positive numbers, not flipping the sign. And so what's interesting about that, there's a couple of interesting sort of, takeaways I see. One is that only one of those solutions is one that a human would have thought of. I wouldn't think I've been given 2 numbers to multiply by to get 1. I wouldn't think of using 2 negative numbers to do that. That wouldn't have immediately jumped out at me. But neural networks can find solutions that are very unintuitive to humans. And the other side of that is also that neural networks don't tend to find the simplest solution that maybe humans would immediately jump for, which is to make both of those values equal to 1, to make theta 1 and theta 2 both equal to 1, so you're just multiplying by 1 the entire time. That's not something. There's no obvious reason for neural networks to do things the simple way, and so if they can avoid doing things the simple way, they'll do it. So I think that's another nice lesson about the way neural networks and machine learning work that you can take from this simple example. The other kind of fun thing about this is if you look at those, they've got this nice shape. They've got this nice hyperboloid shape, those solution values in green in that chart. And that is, it's not a coincidence. I can take any solution. I can get another solution by multiplying one weight by a value a and the other weight by a value 1 over a. So that allows me to move along that curve there, or to switch sides if I use a negative sign. And so there's a very clear algebraic and geometric structure to this set of solutions. And that's something that generalizes to more realistic settings as well. So for rectified linear networks, if you make them big enough, they actually have that same algebraic structure. It's called a Lie group, and it's in fact a Lie group based off of the linear group. And so, so long as your network is really, really big and uses rectified linear units, then it will have something like that. You can do the same thing where you switch between the possible solutions in that fashion. The other thing is that those were essentially two separate basins. So what I mean by basin is if you look at those two sets of solutions, they're separated by a hump in the middle. The hump isn't that high, especially relative to the really high values of the loss, but there is this nice hump there that would be hard to get over with gradient descent. And so solutions in different basins can indeed have very different representations and sort of performance, even when they're separated by only a small barrier. So this is something that people have found by looking very closely at ensembles, or at least smartly ensemble neural networks. And then also I used a sort of high dimensional version of this same problem to improve techniques for finding zero gradient points of neural networks. So finding all the places where the gradient is zero, they're called critical points of the loss. And it's something that's really useful for understanding optimization. I used this multiplying by one example and its higher dimensional analogs to understand the problem of finding critical points better and to develop better solutions. So in general, the takeaway here to remind is that you can use simple problems like this one to build your understanding of how a complicated thing works. Useful ideas and technologies like neural networks are usually compositions of simpler pieces or scaling up those simpler pieces in some way. And those simpler pieces tend to admit base cases that are particularly intuitive or easy to understand. And so the last I guess the last thing is, of course, you want to combine that with pathological counterexamples. So, we've got an example like this where things are all looking nice, working nicely, and things are very straightforward and easy to work with. Then you've got your pathological counterexamples like the memorization task. And then you've got this nice 1-2 punch for tackling difficult concepts. And this general approach, I think, applies to things not just machine learning, but more broadly in both software engineering and in math. So I'll take a second to answer some of the questions that I saw in the chat there. So one question, what kinds of problems where JAX is better suited than other frameworks? So that question, that's an interesting one. I think right now, JAX is more suited for if you want to do fast math that isn't well handled by the other like neural network GPU acceleration frameworks. So it's if you want to do things that it's going to be something weird that other people in machine learning are not doing. So if you want the Jacobian of your neural network, which is like the gradient, but for the outputs of the neural network as opposed to the loss, that's something that you can do really well and with it's well supported in JAX in a way that it for a long time was not supported in other frameworks. It's sort of an inheritor to AutoGrad in a lot of ways, if you're familiar with AutoGrad, which was the automatic differentiation software, unaccelerated automatic differentiation software for a while there. So I would say what's most useful about JAX actually is that it's very principled and very thoughtful on a computational level. It's all about composition. It uses a lot of ideas from the theory of functional programming and from essentially category theory and these branches of abstract math. And while it might not necessarily help you directly being able to program things in JAX, the kind of mental exercise you get from it is certainly helpful. I felt like I learned quite a bit just by changing around the way that I was thinking about the various functions and pieces of my neural network pipeline. Then the last question, could you train something like a language model that has a more dynamic structure that's not neatly divisible into layers? Absolutely. Yeah, you might run it if you're sort of overriding a value over and over again. You might find that you need to write it slightly differently in JAX than you would write it in a different programming paradigm, in a different more Pythonic paradigm like PyTorch. But you can certainly do it, and you'd be able to make things, I think, very fast pretty easily.